method and exact equations. You're familiar with substitution while solving basic equations, where possibly you had e to the 2x plus, I don't know, 5 e to the x plus 6, and then you had it equal to 0, and then you use the u substitution as u equals e to the x, which transformed this equation into u squared plus 5u plus 6 equals 0, and then you can factor it and then bring back substitution and so on. So that was the first level of you guys using substitution. Then you upgraded in trig, right? You had a double angle or a half angle or something. You substitute the 2 theta with x or whatever, solve the equation, and then figure out answers. And then later on in calculus, you had the u sub for integration, where you were figuring out the proper substitution on your own so that you can solve the integral. So something similar like integral of 5x plus 6 raised to the 12th power dx, right? And you said u equals 5x plus 6, and then du equals 5 dx, and then you go and you solve from there. So all of these examples are from your, should I say, past life. Now that you're taking differential equations, we're going to have equations of the first order that look similar to the ones that we did last time, except they don't quite fit the form of the first order linear, meaning y prime plus pxy equals qx, and they're not separable either, so none of those two methods work. But with the clever substitution, you can reduce that equation back into either separable equation or equation that you can solve by the method, right, last time with the integrating factor. So I will go through the example to explain. So we have, I'm going to start writing this as, so y prime is equal to x plus y plus 3 everything squared. So this is, I know this is done in textbook, but I can just quickly show between these two. We'll do some of the homework examples as well. If you compare these two problems, right, you know that if you are to square this out, you're going to get 9 terms, and some of those will be y squared. There is no way that you can actually put this equation in the linear form, first order linear form, because you have that square on this part, right? So what we are going to do is we are going to try and use substitution. I'll write the theoretical part after this example. So you can, with a clever substitution, you might be able to deal with this. So you are going to try and change your variables and then see what comes out of it. So you will, like over here, you for 5x plus 6, you said if all of that was one independent variable u, then I can quickly integrate u to the 12. It's easy. So you will do the same thing here. How about x plus y plus 3, all of that to be a new independent variable, and then you have to mess with dy dx. So this is over here dy dx, right? And since I want to create, let me just write it out. So if I want to create this independent variable v to be x plus y plus 3, right? Now I can plug that easy back into the equation, right? It's just going to be v squared. But the issue is that I have dy dx, which I also have to change. So I will solve this equation for y, right? And then I will differentiate. So y is equal to what? It's equal to v minus x minus 3. So now all I need to do is to differentiate everything, and once I differentiate, plug everything in, and we'll get. So what's dy dx? Is But remember that the v is also the function of x. Right? -1, -0 for 3. V is the function of x, guys. So we actually have to acknowledge that and do it. So now, what do I actually get? If I plug all of these in now, plug in, instead of dy dx, I'm writing dv over dx minus 1 is equal to v squared. So now what you see that is dependent variable y changed into dependent variable v. And I can move 1 to the other side. And now this equation is separable. So by utilizing this substitution, you got the separable equation. Again, we are starting with something that we don't like because we can't separate the x from y, from 3. Everything is squared, everything is together. So because we don't like that piece, right? Usually when well, not usually, now that I teach Calculus 1, I say search your feelings, right? Find what you don't like. And you don't like this piece here. You know the derivative. So that's the one that becomes that v. Why am I not using u? U was kind of level 1, right? Substitution for Calc 1. So it's like a next level, right? So I'm replacing this with the v, and the v is technically now a function of x and y, right? And we have that v is a function of x, so when I take the derivative, right, derivative of v, but I'm taking it in respect to x, because remember, I want to figure out what dy dx is, which is the reason why I solved for y. And so y is given in terms of v and x, and then I have to know that the v is also, you have eyes, you see it, the v is the function of x as well. So now when I'm taking the derivative, the dy dx would be dv dx minus 1 minus 0. I have dy dx, that goes here, which is that, and then instead of the mess, I have v squared. So now move that 1. It becomes a separable equation because you can put dv over, dv over v squared plus 1 equals to just the dx, and then we integrate both sides. What do we get on the left? Very good. That was awesome. No, I'm serious. Equals to x plus c, right? X plus c. So now you can go back and plug in what v was, which is inverse tangent of x plus y minus 3, or whatever the hell it was. Yeah, x plus y plus 3. Equals to x plus c. And you could take this further because you can apply tangent on both sides, get x plus y plus 3 equals to tangent of x plus c, and then subtract x and subtract 3. So y as a function of x would be the tangent x plus c minus x minus 3. And this is a general, obviously, solution, right? It's a general solution in the sense that you have plus c. If you have initial condition, you will plug all of that stuff in and you will figure out what the value for c is. Again, that c is not there for decoration. You must have it because it drastically changes stuff. It's no longer just shift up and down. It could, in this case, what kind of shift is it? For tangent? Shift, well, if c is positive, right? So yeah, it's left-right, right? Depending on the value, whether it's positive or negative. So yeah, right? It's going to be horizontal shift within the tangent. So we have to be careful about those things. Now, why does this work? Well, because of chain rule. And we saw that chain rule up there when I took the derivative of y, which gave me right here. For those of you that have a little trouble with that stuff, this derivative between these two, I'm taking the derivative of v in respect to x. The derivative of v is 1, and then because x and v are not the same, followed by the chain dv dx. So I'm going to follow the same notation. So if we start the problem in general, this is just a theoretical background for it, derivation. So if you start with some general function, f of x, y, you're familiar with this notation from calculus 3, and you introduce another, they use alpha, you introduce a substitution alpha of x, y, then you will solve. This is like a procedure. You solve for y, which would be some different function, and this function is in terms of x and the v. So your old y, which was the variable, the dependent variable, now v takes that spot, so you have x comma v rather than x comma y. So this transformation works this way every time. And then you will plug this, it gives you the chain rule, and you just integrate both sides. I mean, if it's separable, if it's not, then you will have to mess with first order linear, right, with integrating factor. So it can be solved. I'm just going to say this, and then we need to differentiate. So dy dx, to get the dy dx is equal to all right, partial derivative of beta function divided by partial derivative of x, so dx dx. Oops. And then you have the partial derivative of beta in terms of v, and then dv dx. And that's that dv dx from the chain rule that was a leftover for our substitution. Because remember, your goal is to transform dy dx into dv dx, so everything is the same variable. All right, so that's technically how it works. If you know how to read these formulas, then the procedure is there. Let's do another example, something maybe from homework. The other examples that are given in the book you can read, right? You know all the letters and stuff, and numbers and operations, I hope. Scroll up a little bit, sure. No more. I failed at being terrible, actually. That's new. Let's pick one of these with square roots, I guess. This one looks awful. I have no clue how to do this, so let's go figure it out together. Problem 12. It says x, y, y prime is equal to y squared plus x times the square root of 4x squared plus y squared. Wonderful. Keep this one for the final, right? No? All right. Well, you're not going to get anywhere by staring at it, right? So what we're going to do is we're going to try. So there's a lot of stuff going on in the problem, but you zoom in on one and you try with that, right? Which would be the stuff under square root. So let's try and define, because that should be kind of the go-to. There has to be a bulk somewhere of some stuff, in this case under square root. So I'm just hoping that that's the one, because as I said in the previous book, they actually give you the substitution, so you just grind through Calc 1. But in this case, you don't get it, so you have to figure it out. Let's try v equals 4x squared plus y squared, and then go through the entire procedure. Hopefully it goes into either first order linear or separable. So, ooh, it doesn't work already, right? You can't solve for y. Right? Right. So, abandon. I'm not gonna erase it. It's just it didn't work. I'll just say can't solve for y. Can't solve for y. What's the next thing that we could do? Well, how about we divide through by xy, right? Would that help? Let's see. If I divide through, I know I'm losing that 0, 0 trivial solution, but we can add it in. I have y over x plus x and x will cancel, and I have a square root. I shouldn't be doing this, but I am. Divided by y squared. Sorry, divided by y only, not y squared. And if this y undergoes the square root, y becomes y squared, right? So look how beautifully this equation transferred into something that is nice. You see this? So you see there is y over x and there is x over y. Stuff is squared too, so. So now, dy dx is equal to y over x plus square root of 4 x over y squared plus 1. I like this. I like this a lot because I have y over x and x over y. So now we can choose our substitution and then work with it.
Can you take the square root of that? Because the form goes with 2, it would be x over y and then something.
Nope, because of the plus 1. Plus 1 is not allowing.
But you take the square root of plus 1, don't you?
Yeah, but I can on separate, but not in here, because there is this plus is ruining everything. And you can try that. I mean, think about it. 9 times 4 plus 1, right? How much is this? Well, 9 times 4 is?
36.
Plus 1 is?
37.
So we know the answer is 37. If you take square roots, it's 3 times 2 plus 1, and the answer for that is not root 37, right?
All right.
So that's why we can't, right? You find one counterexample, whatever, right? It won't work.
All right.
So we can't take that square root. Cool. All right. So now, what now? What now? What's the substitution? Want to do square root? U equals 4 over x over y squared plus 1. Can we solve this for y? Should be able to, right? So now there will be a square root over there. Why am I using u? Not in Calc 1 anymore. So monitor my VUs. Y goes up, this goes down. It becomes 2x over square root of v minus 1. What's its derivative? We need that one as well, right? We're hoping for a whole bunch of stuff to cancel. You power through these problems. So what's dy dx? Anyone? Quotient rule, square the bottom. Put the bottom here, times derivative of top, minus, copy the top, times derivative of the bottom, which is where all the crazy stuff is. What do we have? We have 1/2 times the v minus 1 squared, and then times the derivative of the inside, which is dv. I just don't have room for this. I did not plan it well. There is a dv dx in the chain rule. Since you are listening to this, you know what is there. So solve the algebra for this and see if we get anything normal, right? The 2.5 dies, and we have dy dx equal to 2 square root of v minus 1 minus x v minus 1 squared dv dx divided by v minus 1. So we can plug this there, right? Combine it or divide by it, whatever you want to call it. So dy dx is equal to 2 over square root of v minus 1, and then over here one of these will cancel, so minus x v minus 1. Oh no, that was supposed to be 1/2 over there, right? Negative 1/2. Is that true?
Yeah.
No, I just... Oh, I stopped writing because it was the end of the line. And I just didn't finish writing. So yeah, that's the... So you look over there, that's supposed to be negative, right, when you differentiate. So negative 1/2, and then this, dividing it's going to be negative 3/2. Is that right? dv dx. Plug all of that in along with the substitution, and then clear even more algebra. Homework is going to be wonderful. Just, you know. But then you have 5 days. Yeah, this is definitely not fun doing this way, but let's power through.
Do like the product rule, chain rule instead of quotient rule?
Sure. Yep. Would that make it much better? You have y equals 2x times v minus 1 to the negative 1/2, and you do the product rule for this. Well, you have to get the same answer, so the derivative would be dy dx is equal to, copy the first one, derivative of the second one would be negative 1/2 times v minus 1 to the negative 3/2, and then plus times the derivative of the inside, which is dv dx, and then you have plus 2 times, copy the second one, which is v minus 1 to the negative 1/2. So I don't think you're actually gaining much, you know, but again, it's differential equations. Do it whatever way it's easier or makes more sense to you. But I'm getting the same thing. 2 over square root of v minus 1 minus x over v minus 1 to the 3/2. Is that what I had earlier? Yep. If I simplify them, it's exactly what I get. Oh, I forgot the dv dx. So either way, I get the same. So this one would actually lead there as well. All right. I have dy dx. So 2 over root v minus 1 minus x dv over dx. Now, I'm still not sure if this is going to work out. If it doesn't work out, we change the substitution. There's something else that I have in mind, but let's see how bad this can get. And I have what? Y over x. Okay, so now we substituted this because we found the derivative, this mess. There goes instead of this. I put equal, and now I have y over x. Observe that I have x over y. So 2 over the square root gets plugged in for that one. There's equal sign here. So this is the derivative you just got. And then this is the equal from the differential equation. This is it. So you're now plugging everything in. And then you have plus square root of v. That's all you have. You need to get dv dx alone to get it in the form of the differential equation. So what you can do is you can multiply first by the square root, and then shove. Well, first of all, these two terms completely drop, right, because they're identical. And what you get is negative x over v minus 1 to the 3/2 dv dx is equal to square root of v. And you multiply both sides by the flip of this, so you so to get cancel it. So dv dx is equal to negative x over v minus 1 to the 3/2, and then there is a root v on top. Now this is clearly a separable equation. Again, why do I say clearly? You have all multiplications everywhere. You know it's not separable if you have +1 or something like that that prevents you from separating these from x's. But in this case, everything is separable because you keep dv, and then what was on top goes on the bottom, and what was on the bottom goes on top. And you have on the other side negative x dx. Yes?
Are there multiple substitutions that you could use if there's not one?
The answer to that question is yes, but we'll stay away from it because one is messy enough already. In some problems are right. I mean,
I just meant if you didn't come with this conclusion for the substitution.
Yeah.
Right.
If the stuff gets really ugly, most likely it's wrong. If it gets really ugly, I powered through and look, everything's simplified and it's beautiful, right? But it could get really ugly. Oh, you're right. Oops. Yep, sorry. I did not put, so when I'm getting the derivative alone, right? When I'm getting this derivative alone, this negative x, so root v stays where it is. It gets multiplied by square root of v minus 1 cubed, and then it's divided by negative x. Yeah, thank you. It's still separable. It's just I have stuff in the wrong spot. So now I have no coffee. Right, cool. So now I have the dv divided by root v minus 1 cubed is equal to dx over negative x. The right hand side is easy, right? It's ln, negative ln x. The hell are we going to do on the left? Right? So how do we integrate that? Of course, Wolfram off, exactly. So maybe now is a good time to kind of figure out what kind of U sub we can use, or something else. I might, yeah. There has to be something nice that we can do. Unless there are, there is some other error somewhere else, which would I have? No, that would be +1. All right. So, integrate. The other side is easy. Just want to see if they put something into this section. So homogeneous, sure. Initial value problem, we'll do that. So Bernoulli equation, does it have? No. All right, let me try same problem. One more thing. I'm not going to erase anything. So same problem. I want to use the specific substitution, that it's not intuitive. You have to know it, and hopefully you will use it anytime. You will try it, and if it works out, it's great. And it's the substitution for homogeneous equations where you get v equals y over x. So let me do the same problem. What was the problem? dy dx. Oh no, that was crazy. I'm going to actually just that simplified form. That's what I'm going to start. So dy dx is y over x plus the square root. For x over y squared plus 1. So we are doing the same problem, except now I am forcing this substitution upon you. Y over x. So deal with it, right? So now, if you solve for y, y is going to be, it should be v. Yeah, it's funny for you, but now I had to erase it. So it's vx. V is the function of x, so we have the product rule. So dy dx is going to be copy the first times the derivative of the second plus copy the second times the derivative of the first. And we plug all of this. Hopefully that fixes it. So dy dx is given as, let me just go here, say plug in. And that one is going to be dy dx, it's v plus x dv dx is equal to y over x. We said that's v, so v plus the square root of, and here is the now 4 over v squared plus 1. Because y over x is v, then x over y has to be 1 over v, right? Everything was squared, so that's what we get. Now v is die again, and we have separable equation. Awesome. So we have x dv dx equals to square root of 4 over v squared plus 1. Now we don't like this v squared in denominator, so I'm going to multiply both sides by v, just v. Try to clear it out. When single v undergoes the square root, it becomes v squared, and that is going to kill off v squared in the denominator. So what I'm going to have is x v dv dx equals to square root of 4 plus v. Now this is separable equation. I have v dv divided by square root of v plus 4, let's swap that, is equal to dx over x. Oh, much better, right? So when you see in the problem after that algebraic manipulation in the beginning, you get either x over y or y over x, like we had in two instances. We had it here and here. Then we force this particular substitution, and hopefully that works. There's a fair amount of memorizing procedures and things in this course, so hopefully you guys will be picking up patterns. So I tried and I failed to do the problem, just through intuition and see if I can use this or use that for the substitution. It clearly didn't work out because I had no clue how to integrate this, right? So in that case, let's try this method, and it worked. So what do I do? How do I integrate this stuff? What do I do? Oh, wait, that's a square, guys. So v squared plus 4. When v goes under the square root, it picks up a square, so it's v squared. So v squared and v squared cancel, it leaves the 4, but 1 times v squared is v squared. If you didn't see what I did, is I added this square and this square. I added those two squares because I missed them. Phew, sub. Oh my goodness. We have v squared and we have v, right? So u is equal to v squared plus 4. And then du is equal to 2v dv. I don't have a 2, so we'll fix that issue by adding a 2. And I have 1/2 integral dv over root v equals to ln absolute x plus c. So 1/2, that's a 1/2, negative 1/2, positive 1/2, so 2 root v ln x plus c. These cancel, and you have your v to be ln absolute x plus c, everything squared, if I did all of this correctly. Oh yes, oh my god. Kill me now. I gotta change all of this now. Integrals in terms of u, yes. So now, I plug in the u, which is v squared plus 4, is equal to ln absolute x plus c. And finally, I plug in v squared, which was y over x. And there it is. Another one? Anyone wants to go home? But you can't. No, you can. What kind of solution? Yeah, it's general, right? Because we have plus c. But how do we call this particular, when line looks like this, when I can't solve for y? How do we call that? Nope. Yeah, but it's not a function, right? We have y squared. Implicit form, yes. It's implicit form. So something that you write, like a previous example, y equals everything in terms of x, that will be explicit form. You are used to functions in explicit form all the time, y equals f of x. When you cannot separate y, it's implicit form. And many of the answers that you get in this section will be implicit form. So I think book has, let me see. Here is one. Here's another one. So book has at least 2 examples. I don't want to flip through all 15 pages, but book has at least 2 examples that have implicit form as the answer. So it's okay. Yes?
Because I know I'm going to do this during the test. Why can't you move x squared and 4 over?
You can.
You can?
Yeah, but you're not going to get y equals. You're going to get y squared equals. And if you take square root of both sides, you're going to get plus minus square root.
Okay.
Right? It's like an equation for the circle, x squared plus y squared equals 4.
Yeah.
Right? You move x squared, you get 4 minus x squared, and when you square root both sides, you get square root of x squared plus 4 and negative square root. So that's a half of the circle, and the negative square root is the other half of the circle. So each one of those independently are functions because they, right, the semicircle passes the vertical line test. But when you write them both on the same line with a plus minus square root, it's no longer a function. Therefore, this is not a function, it has a y squared in it.
Yeah.
Now, you can get any kind of squiggly lines with this thing, right? You end up with y cubed and so on. They can have this, right? The loops like that and stuff. So these curves are going to look whatever mathematically gives you when you type it in. Okay?
So basically you stay that way because of y squared?
Yes.
Okay.
Yes. Or I had something else that I can't separate. Sometimes you're going to have maybe, let's say, sine of y over here, but then you're going to have a y somewhere else.
Yeah.
There's no way that you can, or one y is free, the other one is buried in ln or into e. There's no way for you to factor it together into a single y and then make one y and move everything away. So anytime when you have non-linear y is when you definitely can't fix it. Like y squared, cubed, 4th, 7th, and then sine of y, e to the y, combined with some other y somewhere else, right? If it's only e to the y, you just ln both sides, right?
Yeah.
If it's sine of y, you just inverse sine both sides. But if you have sine of y and then another y somewhere else,
Yeah, on the other side.
you can't combine them into a single one.
Okay.
Which is interesting because today when I taught algebra, that was the topic of when can we express it that way and when we can't. That was, we were solving for variables in those. Nothing like this, obviously, right? But, yeah. So it's differential equations. I just write 2 lines and I just finish this. And then I walk away. Let's take a look at something else. This should be fairly bad because it has E in it, I guess. I don't know. Ran out of ink. So 3y squared y prime plus y cubed equals to e to the negative x. Yeah, no clue. So, no, I got some cash here, guys. Solve this problem by the time. Well, you know that every problem should start by getting this y prime along, right? So see if you free that up, see what else you can do. I'm gonna do that.
part? Impossible? Which one is it? Should we just move on?
Just have to restart the software. So dy dx plus y over 3 is equal to e to the minus x over 3y squared. Tears or no tears? Yes?
Well, first I got
Y over 3, right?
well, I did y prime equals e to the negative x minus y cubed over 3y squared, and I did v equals e to the negative x minus y cubed, and everything here is minus.
Oh, nice. Thank you. I don't have to hunt for it. So you said e to the minus x minus y cubed divided by 3y squared, and then v was e to the minus x minus y cubed. Okay, thank you. So we solve for y. Well, y cubed first is equal to e to the minus x minus v. We can do implicit, right? So 3y squared dy dx is equal to negative e to the negative x minus dv dx. Awesome. We plug everything in. So, well, I have to move 3y to the other side. So I have, well, let's first do that. So dy dx alone is negative e to the minus x over 3y squared minus 1 over 3y squared dv dx. So now I have, so now I plug in. So instead of dy dx, I have negative e negative x over 3y squared minus 1 over 3y squared dv dx equals to just v over 3y squared. Now multiply through by 3y squared, they all go away, and you are left with negative e negative x minus dv dx is equal to just v. And then move everything to the right, right? Well, move it twice, right, because of the minus in front. And anyway, I don't want to write it 15 times. It's going to be v minus e to the minus x. Right? Does this make sense, everyone? Now, what kind of equation is this? Hello? Can't separate? has a negative, right? Minus e. Yeah, it's gonna be the first order linear differential equation that we have to use integrating factor for. So v is on the wrong side. We have dv over dx minus v is equal to negative e to the negative x, and this is where we use integrating factor. So use integrating factor. So what is my p of x here? Anyone? -1, thank you. And the q of x is obviously negative e to the negative x. So what was the rho of x formula? E to the integral px dx. Very good. All you need to do is to write this 5,000 times. You're going to remember it. So I hope without me writing 15,000 steps, it's just that, right? Are we green? Good. So we are multiplying. We're multiplying that through the equation. So I have e to the minus x times dv dx minus e to the minus x times v is equal to negative e to the negative 2x. Are we agreeing on this? Now, this is the one that collapses into the product rule, right? So if this was our g prime, then this was the g, which means that this was f prime and this is f. So it collapses into e to the minus x v, the derivative, equals to minus e minus 2x, at which point we hit both sides by the integral. On the left-hand side, derivative and integral cancel each other, so all we get is e to the minus x times v. And on the right-hand side, I integrate this. I will get negative and negative. They cancel each other out, so I have e minus 2x divided by 2, and then plus c. So e to the minus x will go and kill one of the e to the minus x's. So I have that v of x is equal to 1/2 e to the minus x plus c. But then you know that v was a mess from before, which you have to plug back in. So we go 3-4 pages back. It's e to the minus x minus y cubed. So e to the minus x minus y cubed is equal to 1/2 e to the minus x plus c. So now this guy goes to the other side. When you subtract 1, it gets negative 1/2. So minus y cubed equals to negative 1/2 e to the minus x plus c. And then you do the times negative 1. You get y cubed is equal to 1/2 e to the minus x plus c. Now see, this time plus c, even though you're multiplying by -1, it doesn't really change. It doesn't matter. That is the general solution for the problem. Yes? Yes, I can. Yeah. It's not going, it is a function in this case, right? Because it's a cube root. So cube root, there's no plus and minus, so 1/2 e to the minus x plus c. If that makes you happy and makes you smile in this class, please do. Your happiness is our primary concern. Thank you for traveling with us. All right, cool. So I did, well, with your help, 2 or 3 examples, and you guys have another 20 that you can practice at home on this topic. The next part of this lecture is the exact equations, where the exactness condition comes from the fact that mixed partial derivatives are the same. And you can integrate. I know. It's a long day and it's too hot in the classroom. Dying. So nice outside. Plus they have actually food in front of the art gallery set up. Yeah, see everyone now has to go. So is this the time for a break? Yeah, okay, it's time for a break? All right, fine. So we'll come back, and second part of the lecture when you come back from the break. 3 minutes. I'll stop the stream and I'll restart.